Today I'm going to be talking about LeetCode question number 332, Reconstruct Itinerary. So you're given a list of airline tickets where tickets at index I is equal to from to a represented departure and arrival airports of one flight. Reconstruct the itinerary in order and return it. And all the tickets belong to a man who departs from JFK, so JFK will always be a starting point. Thus the itinerary must begin at JFK. If there are multiple valid itineraries, we should return the itinerary that has the smallest lexical order when read as a single string. So for example, if the itinerary JFK and LGA has a smaller lexicographical order than JFK and LGB. So basically kind of alphabetical. When you assume all tickets are form at least one invalid itinerary, you must use all the tickets once and only once. Okay, so for example here, so we start at JFK, and there's only really one way to go, so UC, LHR, SFO, SJHC. Yeah, that's pretty much the answer here. And if you look at a more difficult example, we have JFK, okay, and then we could either go to Atlanta or SFO. But since we want to visit them in less graphical order, we're going to visit Atlanta first. Okay, so JFK to Atlanta, and then Atlanta to SFO. Okay, this edge and this edge, and then SFO back to Atlanta, and then Atlanta back to JFK. And then JFK to SFO. Can't forget about this edge here. Okay, notice we went to Atlanta first instead of SFO because Atlanta is in lexicographical order. Okay, so basically what we're doing is getting a node and going deep into its children and to find out the children's children and so on. So this is a good candidate of DFS. Okay, and basically how we're going to store these the itinerary here is an adjacency list. Okay, let's look at a harder example. So we have JFK here, and then we go to, let's say, Atlanta, and then SFO, and from SFO back to JK. Okay, so what are we going to do here? Well, according to our lexicographical order, we visit JFK to Atlanta first. Okay, but unfortunately from Atlanta, we're stuck here. We don't, this is our last stop. Atlanta has no outgoing flights for this person's itinerary, so we can't actually go to Atlanta first, otherwise you'd completely miss this SFO. So what we gotta do is instead visit SFO first, okay, and then back to JFK, and then to Atlanta. That way we're able to visit this edge, and this edge, and lastly this edge. And that's the whole itinerary there. Okay. So that's basically how we're going to go about it. Again, these are stored in adjacency list, and since they're in lexical order, we got to store. So for this example here, JFK, this is going to be the adjacency list. We're going to store them as this, Atlanta, SFO, not SFO and then Atlanta, okay? And the SFO is going to be JFK, and then Atlanta obviously has no children here. Okay, so yeah, that's basically how we're going to go about it. So in this case, when we visit Atlanta, how do we know, or how do we know when to completely stop? Well, we're basically going to store everything in a result array here, and we basically stop when the length of result is equal to the length of tickets plus 1. Okay, why do we stop here? The result array is going to basically store the output here. So why length of tickets plus 1? Well, it makes sense because if we have like this itinerary, we have the length of tickets would be 1. Okay, it'd be like A, B. Okay. And then in our output, what we want to have is A, comma, B in our output. So if we have 1 ticket, we'll have 2 outputs. And similarly, if we have this guy, we'll have 2 tickets. So this will be B, A, okay, and then 3. Okay, so it's kind of intuitive there, where length of tickets is the number of airports in the output. And yeah, that's basically how we're gonna go about it. And in the case where we hit an airport here, where there's no outgoing edges, here, but we still have unvisited edges, i.e. the length of result is not equal to tickets 1, and what we gotta do some backtracking, okay? So for example, if this is getting messy, but if there are results arrays JFK and then Atlanta, and then we find out we're stuck, what we gotta do is pop Atlanta from results array and then visit SFO. Okay, and while we're visiting each airport's child, we're gonna also pop from the adjacency list here. So for example, JFK to Atlanta, we pop Atlanta, then we found out we're stuck at Atlanta, so we can't exactly visit it first. So we push it back in and then visit SFO next. Okay, and we're going to systematically remove all the visited airports from each of the other parent airport. Okay. And the time complexity of this is, since we're doing backtracking, that kind of means that we have to visit each node and edge at least once, or sorry, at least we can potentially, visit each node and edge at least twice. So the time complexity would be O B plus E. Okay, it's not a simple DFS traversal. Okay, since we're backtracking, like here we backtracked. We visit Atlanta, then we backtrack, then visit SFO, and then we'll visit Atlanta again later at the very end. So basically Atlanta was visited twice, so this will be OB plus V squared. Okay, to code it up, so first off I'm going to build my adjacency list here, which is going to be a dictionary. Okay, and then populate the adjacency list with the tickets, the parent and then child. But first what I want to do before I build my adjacency list is sort tickets. Okay, why do we want to do that? Well, we want them in lexical order, and what we could have done instead of is an adjacency list for each of the nodes children in the adjacency list, sort the children, but it's actually easier to sort just the tickets itself, okay? And it makes sense. Why does it make sense? So if we look at this example here, tickets.sort, we have JFK SFO, JFK Atlanta, and since these two JFKs are the same, what's going to do is sort by the second value here. So this guy will come before this guy. Okay, and then as we're iterating through tickets to build up the adjacency list, we'll visit Atlanta first and then SFO and then push that in our list of children for the parent node. Okay, so for I in tickets, if the parent not in the adjacency list, what we want to do is add it. Okay, and then add a child. Okay, and that's pretty much it. And then now what I'm going to do is initialize my result. So initially it's going to have JFK in here. Now I'll define my depth first search. And what this depth first search is going to take in is let's call it the airport. Okay. And now whatever base case is here, so if the length of result is equal to when tickets plus 1, then return true. Also, if airport not in our adjacency list, a reason it could be not an adjacency list is it has no outgoing edges, so like SJC here, you don't see it as the parent at all. Okay, and what we're going to do here is return false, and now what we're going to do is get the children for that airport node. So equals okay, so children is going to do that, and then what we're also want to do actually is create a copy of children. So this is how we're going to create a copy here. So why do we create a copy? So I'm going to iterate through children. So for fishing value okay, so I'm creating a copy because this children directly links to the children for this airport here. Okay, this is just a plain old copy. So while we're recursively calling depth first search, we're gonna, as I said before in our drawing, remove children, remove the child from airport's children list. Okay, to show that it's been visited. And as we're kind of popping from this children's list, we still want to iterate in case we need to backtrack and re-add it to children. We're going to be popping and adding from here a lot, so it's best to have an original copy where we can properly iterate through all the children. Okay, so what we're going to do here is, so we want the index and then value. So what I'm going to do is result dot end val, and then children dot top add position index, and then call DFS. And if it's true, meaning we visited all the edges, is equal to length tickets plus 1, then we're just going to stop there. Okay. Otherwise, that means we still haven't visited all the nodes and edges, all the airports and the flights. So that means we must have gotten stuck at a dead end, okay? Like if this edge weren't here, just imagine we got stuck at Atlanta dead end. Alright, I guess this isn't a good drawing, but from my previous drawing before. So what I'm going to do now is actually reverse what I did here. This is the backtracking now. So result dot pop and children dot insert at that index. I want to insert my val here. Okay. And then return false. Okay. And now finally what I'm going to do is call DFS that I just made. Initially JFK. And then return my result here. So I'm going to try a dry run. Okay, I'll use more test cases here. And I'll see it. Okay, great. Thanks for watching.